We're very happy to be here this morning to talk about robust routing for battery electric vehicles. And we're very pleased to have been selected as a semi-finalist for this award. So this is a collaboration between Ford and MIT. I'm Daniel Reich from the Ford side.
And I'm Dimitris from MIT. Glad to be here.
Electric vehicles have some very nice benefits over conventional gasoline engine vehicles. So one is emissions. It's a clean ride. It's clean environmentally. So that's a great benefit. The second is energy independence, and this is a national security issue for us. We import a lot of the oil from foreign countries that we use for our gasoline. When you're plugging in your vehicle to charge it using our electric grid, that's something that we generate domestically. We have many options for doing so, which brings us to the third point, which is fuel costs. So the fuel costs, when we pay for electricity, stay within our own economy here in the U.S. When we're paying for gasoline, some of that money is being sent outside the U.S. So that's as a nation. But on a personal level, if I go to plug in my vehicle and I charge it up at home, it's going to cost me a lot less than it would to buy a comparable amount of gasoline at the gas station. So these are the first three benefits, and the last one is convenience. So you may have had the experience, you get up in the morning, you're running a little bit late, you get into your car, you're ready to go to work, and you notice you're low on gas. You have to make a stop, fill up a bit, it takes a few minutes, and it's not particularly convenient. With an electric vehicle, you're all set. You plug it in at night, you unplug it in the morning, and you're ready to go. So because of all these great benefits, our nation has a plan. We want to have 1 million electric vehicles on the road by 2015. And President Obama outlined this in his 2011 State of the Union address, where he noted of particular importance the reducing our dependence on foreign oil, the national security aspect. So at Ford, we, of course, want to support this mission. We think it's an important one. So we've developed the Ford Focus Electric. And here's a short clip on the vehicle.
We've all heard that the age of the electric car is here, and it brings with it many new questions for drivers. Like, how far can I go? And is there a smarter way to get from point A to B? Introducing the 2012 Ford Focus Electric, the first gas-free, zero CO2 emissions passenger car.
Great car. So you heard two important questions.
And I'm biased objective.
They really highlight the difference here between an electric vehicle and a traditional gas engine. Thinking about how far can I go and what's the smartest way to get between 2 points. All electric vehicles, they have a limited range. The battery only has so much power. And if you run out of that power, you're going to need to recharge. And charging stations, they're not as readily accessible as a gas station, where you can find one in every corner. And even if you do find a charging station, it's going to take you a lot more time. It's going to take you probably hours to charge your vehicle. So because of this, there hasn't been such great news on the sales end lately. And you've heard from Toyota within the last month, they're scaling back their plans for electric vehicles. A Nissan executive noted earlier this month the Leaf sales are well short of the goal they have. And as a nation, this goal of having 1 million electric vehicles on the road by 2015 is in jeopardy of not being met. Right now, if you know the numbers, they're in the tens of thousands in terms of the sales. And we need to get that up to 1 million, and we have 3 years to do it. So one idea for dealing with this barrier of a limited range is infrastructure. Get more charging stations. And already at this conference, I've heard several talks on placement of charging stations. So this is a field that's of interest to the OR community, an active area of research, and it's a great idea. It's for good reason. This is without doubt going to increase the utility of electric vehicles. But there's another issue. Oh, before I point that out, 6 states on the map, you can see how many electric charging stations. This is from energy.gov. There's almost none. So we think the first issue that we need to deal with that's really pressing is understanding how to use your vehicle. If you had a big boat, you're not going to get a tiny little car to tow it, right? Similarly, if you want to drive cross-country and you ask me, hey, should I take my electric vehicle? I'm going to tell you, I wouldn't recommend it. I don't think it's a great idea. But there is a great use for electric vehicles, and there's a great use for the Ford Focus Electric. So by a show of hands, how many of you have a daily commute that's under 75 miles round trip? Under 75. Okay, we have almost the whole room here. So you could go back and forth to work with a Ford Focus Electric, no problem. But
sign up afterwards.
Yes. I'll be selling in the hallway. But there's a barrier for selling these EVs. And what we think that really is this anxiety. Consumers they're worried they're going to get into their car, they're not going to be able to reach their destination. No one wants to have to worry. If people are worried, they're not going to want to buy an electric vehicle. And we have to deal with that. And that's what our innovation is all about. It's about a new way of thinking about routing that's geared towards electric vehicles, so we can give people peace of mind. They can get in their vehicle and they can know, no problem, I'm going to get where I'm going. I don't have to think about it. So how are we going to do that? Well, we're going to focus on energy consumption. That's the limit, and we need to be conscious of that and work our routing around it. So the first piece, understanding energy consumption. We have a physics model to do it, and we need to know that's highly accurate. So our second piece is the analytics and the data, where we calibrate. And we're going to show you we have great accuracy. But there's not that much EV data around. There's not that many electric vehicles on the road. And the ones that we have on the road, we don't necessarily have the ability to get all the data from. So we need to understand more than the data allows us to. We need to understand lots of traffic conditions, lots of driving behaviors. And this is where simulation comes into play. So with these first three pieces of a physics model, getting high accuracy on it, and then simulating for other conditions, we really understand energy consumption. And then once we can do that, we're ready to route for the electric vehicle. And that's where robust optimization comes into play. But for those of you who are familiar with robust optimization, you know this is not something you're going to solve quickly on your standard GPS unit or on your in-vehicle technology. These are complicated optimization problems. And if we want to get them instantly solved like people are going to expect from a GPS routing algorithm, we need a powerful processing infrastructure, and that's where the cloud comes in. So the second part of this innovation, the first part is the routing. The second part is making all this work in the vehicle. We need to connect the cloud to the driver, to the car, and we do this with mobile applications and the vehicle human-machine interface. So now, you saw on the first slide, we have a large team of people working on this, especially on the Ford side. And the reason is we need a lot of areas of expertise to tackle this problem. And we have people from vehicle controls to propulsion simulation to the in-vehicle technology and cloud apps that we need to make this work in our vehicles. And then, of course, our analytics and operations research, of which I'm a part. And on the MIT side, we're thankful to have more expertise coming in analytics and OR, and particularly in robust optimization, in which Dimitris is an expert. You may, if you're familiar with it, you may be familiar with his chapters on it. And I'm going to pass it to him to start going through some of the technical detail.
Thanks, Daniel. So the first question we're going to answer is, how far can I go? And as Daniel mentioned, we started with a physics model that tries to understand energy consumption. So what are the ingredients of this physics model? So this is not the time to give you a very detailed introduction to that, but so first, there are forces. There are four types: aerodynamic drag, rolling resistance, climbing force, and acceleration. And energy is, by and large, force times velocity. And all these type of forces, the formulas for them, this is the first part of aerodynamic drag. You observe a quadratic dependence on velocity. The second part is the rolling resistance. You observe that the cosine A or alpha, I'm Greek, is the angle of elevation. The third part, the declining force, there's also the elevation component, and this is the acceleration part. Right? So these are the components of the force. So there are good physics engineering reasons. This is a model that we jointly developed when a student of ours, Matthew Fontana, who's in the audience, visited Ford, and we worked together on that. So this captures the following components: the speed, the time, the distance of the trip, the elevation, acceleration, as well as accessory loads. There are other components that Daniel will talk later about driver's behavior and traffic conditions, but the physics model tries to capture these elements. So, of course, that's a model. Models are approximations of reality. They're not reality themselves. So we calibrate the model using vehicle data analytics. We have data. I mean, Ford has this particular car is in production. We have not gigantic production yet, but there are vehicles that Ford engineers drove. So we have data from 6 vehicles driven in California over a 2-week period, and we have readings every second. The readings are the energy consumed, the speed, and the GPS coordinates. We also have data from elevation using geological surveys, the US Geological Survey National Data Set. We aggregate the data to do analysis. And this is the model I talked to you about regarding the forces, which is a key primitive quantity. You observe, for example, force times velocity, there will be a cubic term. There will be a term velocity times the cosine of elevation and so forth. So we took all this data and we unified it in a way that to do appropriate analysis. And we built various types of statistical models. Here's the simplest of them, and in my view is quite spectacularly accurate in that. So based on this intuition from physics, we try to estimate energy as a function of these quantities. So we run a regression. These are for various elevations, velocities, and so forth. And you observe that the R-square of the regression is 0.92, and the t-statistics are quite significant. Of course, they are not perfect, and there are a few things, of course, we don't account for: the driving conditions, the behavior of drivers. We don't have detailed information on that. And on that front, would like to incorporate these aspects. And for that, the Ford team developed a very interesting innovation, in my view, that Daniel is going to talk about in a second, about how to incorporate driver behavior and simulation, also including traffic conditions. Daniel?
Great. So driver behavior, traffic conditions. Like we said, we don't have enough data for EVs to know all of this. So that's why we're going to use simulation. So coming into the simulation, we have roadmap, traffic conditions, we have driver profiles, and then coming out we have what's called the drive cycle. This shows you how the vehicle's moving. It's velocity versus time. When you combine that with the vehicle specs, so you know how much does this vehicle weigh, what kind of tires does it have, what kind of powertrain does it have, you can use propulsion modeling and then find the energy consumption. If you do this again with the traffic conditions and the driver profiles, then you have a distribution. You really understand your energy consumption. So here's a couple of videos of examples of drivers. Here's a conservative driver. This is like the way Dimitris drives. It's nice and constant speed, lots of distance. He's stopping at the light just like he should. And now this is more like how I drive on the right. Weaving. Whoa, I was weaving, but I stopped. Anyway, I'm going to keep going, and I go through the light when it's green. And I finish this trip a lot quicker. So the aggressive driver is going to do this in about half the time as the conservative driver. And the conservative driver stops for a while, you see at the light. But otherwise, the conservative driver is going at a pretty even speed, where the aggressive driver's speed is going up and down, getting the job done. Okay. So in terms of energy, that makes a big difference. So that's pretty much the picture on energy consumption. Hopefully, you find the story complete. Now we want to talk about the robust routing part, the optimization part, and Dimitris is going to introduce that for us.
Thank you. So at this point, we have built the tools to ask and answer the first question: how much energy do I consume? It's included the physics model, the analytics from the data, and the simulations. So we have a model. Later on, you will see that we built an app that answers this question, and it's now in production. But now we have a model. And the question is, would like to use optimization. And you might say, why robust optimization? And that's what would be the question I would like to answer regarding, is there a smarter way to get from A to B? So let's consider what's the reasonable first step? A deterministic perspective, right? So we'd like what are the things we can optimize? We can optimize speeds. These are we have an underlying network. We can optimize speeds. Vij is the speed on the arc ij. It's within bounds. And selection of routes. So there's a collection of paths, and we can optimize over them. So under the deterministic perspective, what we would like to do is we would like to minimize the total time. This is the trip time from the vehicle, plus potentially some additional time, delays, traffic lights, and so forth. Deterministically modeled for now, subject to energy constraints. Namely, there is a target. This is the energy. E0 is the target we have. This is how much energy we have at the moment. And this is our budget. And we would like to constrain the trip so that the total energy consumed, this is the energy and times the path used, the energy functions are coming from the analytics models, calibrated according to the tools we have told you. So this is a deterministic problem, a shortest path problem with velocity optimization, a nonlinear one, subject to additional constraints on energy consumption. Even though it's not a walk in the park, it's reasonably doable, and we have developed, that's another part of the innovation, we have developed appropriate algorithms that can solve this problem very quickly. So, and we have tested this algorithm from, so I live, I teach at MIT, so my daily commute is about in the order of, I would say, 18 to 25 minutes from Belmont, Massachusetts, where I live, to MIT. I mean, I recognize you don't live in this area, but and these are we took data from a particular software that we utilize that incorporates, in addition to maps, it incorporates elevation data, and these are the 5 routes a deterministic perspective takes. Memorial Drive, Massa. These are all routes that over the period of the year I use. These are not exotic routes. I mean. And I didn't impose these routes. When we run them, these are the output. This is not, we didn't force it. So this is what we get. And this is the trade-off. So this is the Pareto frontier between energy and time. So I told you my trips, when there's not gigantic traffic conditions, are of this order. This is, I think, appropriately calibrated, the model. So we put a target of 152 kilowatt hours. The horizontal axis is in minutes. The vertical axis is the energy consumed. And you observe the trade-offs. Namely, if you want to consume in a deterministic way less energy, you might have to travel sizably more. And these are the possible, what we observe for that particular trip. Of course, we run it in many other instances. This is something I have personally familiarity with because these are trips I take. So at the level of when we put epsilon 0, remember the target of 152, the selected route, we try to minimize time in this case, would be Memorial Drive, and it would be roughly 18 minutes, which is roughly correct. Of course, I don't have an electric car. I have a conventional car, and it's roughly well calibrated. So remember this graph, because I think this will try to show the fundamental trade-off between deterministic and robust optimization. So now, it's, of course, a deterministic world does not take into account that in reality, there are fluctuations in time and there are fluctuations in energy consumption because of conditions that we haven't yet modeled in the model, right? So we ran a simulation in which we took the trip that uses Memorial Drive, the one that deterministic optimization gave you, and we subjected it to random perturbations, right? And what we observe is that the limit of 152, so this is the density function of in simulation of the trip from Memorial Drive, you observe that at the target of 152, 41% of the time, we don't make it, right? 41% of the time. I mean, I don't know about you, but I would not be too comfortable with these percentages, all right? So not too surprising, because deterministic optimization does not take this into account. I mean, it's not does not take into account. It's not, we do the great job, but it ignored the fluctuations. Okay. So a natural idea is to consider stochastic perspectives and in particular, robust optimization. Robustness in this case, in my view, is more important than optimality. You saw what happened with the Toyota story. They cited the most important reason that they withdrew is anxiety. That's why the sales were low and so forth. Not my words, their words. So here's how we reformulated the problem using robust optimization perspectives. Again, we try to minimize over velocities and selection of paths. The worst case, but now what is the worst case? So we have here, this is the total duration of the trip in a deterministic world, but we added the possible perturbations because of, this tries to capture things like a possible accident, a possible, various types of things, right? So we try to maximize over this, so we take the perspective that nature is an adversary, but a bounded adversary, an adversary in which each perturbation is bounded, and the total perturbation is bounded as well. So we try to minimize over the choices of velocities and choice of paths, the worst case that is bounded, that's the objective. And similarly, we take the perspective that now the bound of energy is the maximum of all perturbations. So we are potentially more conservative, right? We are potentially more conservative. This is a robust optimization mode for which in the last decade we have, so my group at MIT has developed a lot of algorithms, and we have implemented, that's also another part of the innovation. A particular challenging part here is to do it fast. And that, it's not the time here, but we have actually developed algorithms of this type. So we solve this problem, and you observe, for example, a parameter gamma there that we can change, namely how much budget we have for uncertainty. So when we solve this problem, it ignored two of the paths. They were not in the efficient frontier, so it concentrated naturally, didn't force it. Three of these paths, these are paths that we utilized also from the deterministic perspective. So this is, just to remind you, this is the deterministic curve. This is the robust curve. And you observe that you've noticed that from a perspective of time, we paid a bit on time duration. You observe that the durations are a bit higher than in the robust setting than the deterministic setting. We'll see later how simulation can clarify the picture more. And you observe that the trade-offs are somewhat different, but at the level of 152, the route chosen would be the Mass Avenue route. Okay? Right. And I would say if this is something to remember from this work, is that, so this is the trade-off of the PDF of the deterministic. So this is the density function of the robust energy consumption. And you observe that the energy consumption is decisively less for that trip. Decisively less. In fact, what is the probability that you will not make it at the level of 152? 0. So in other words, so it gives you peace of mind. That's the key. Of course, there are no free lunches in life. So you pay a bit with optimality. But the price to pay is not that big. So let's see how much to pay. So at least in my opinion, it's not that big. I would be, if I had an electric vehicle, I would be willing to pay this price. So the average trip using the deterministic memorial drive, which by the way, I know that, is about, let's call it 18 minutes and 25 seconds. So the robust trip takes a bit longer, about half a minute longer. So the price to pay is for a bit of a longer trip, you get a benefit of peace of mind. That's the key principle of the story. Of course, we've done quite a bit of more simulations to illustrate that point. So final point is that Daniel will talk about is how to use all this information to build, to deliver a solution for clients.
So what Dimitri meant to say wasn't if he had an electric car, it's when he buys a Ford Focus electric. He'll be willing to forego that minute. So here's how it works in the car. For those of you who have a Ford, you're familiar, Sync My Ride probably. How it works, you have onboard telematics. You get some important information. So in this case, state of the battery, how much charge you have, GPS coordinates, there's other information, and that's going to be sent to the cloud through your cell phone. So it's the driver's making the connection. Then the cloud is going to provide processing power, access to data. It's going to give you the solution and send it back to the driver, again, through the mobile app. So here's the mobile app, and it's on my phone. If anyone wants to take a close look at it later, come up. If you want to download it, go to Google Play, type in My Ford Mobile. You can grab it now. If you have an iPhone, go to the App Store and you can grab it. See how it works. There's a guest sign-in mode, so you don't have to own an electric vehicle to see it. But here's the first app. basically we did this part. This is about the energy consumption we were telling you about, using the physics model, our ability to calibrate it with high accuracy, and our simulation to understand driver conditions. So this is where we're headed, and this is the last piece. A smarter way to get from point A to point B. This is using the robust routing, develop another app. So the driver gets in the vehicle, we tell them the route, they're good to go, no more worries, and we sell a lot more electric vehicles. So thank you very much.